Step outside on a clear day, and the sky is a brilliant blue. But the sunlight illuminating that sky is actually white light, a completely blended mixture of every color in the visible spectrum. So where exactly do the other colors go? As light passes through a prism, it separates into those individual colors based on their specific wavelengths. In our atmosphere, nitrogen and oxygen molecules act like a massive obstacle course for this incoming light. When sunlight hits them, a process called Rayleigh scattering takes over. These tiny gas molecules easily scatter the shorter, choppy wavelengths, like blue and violet, bouncing them in every direction, while longer, smoother wavelengths like red and yellow pass right through. Here's the paradox. Violet actually has the shortest wavelength of all visible light. It gets scattered the most. Based on the physics of the atmosphere alone, the daytime sky should appear entirely violet. The reason it doesn't comes down to a fragile compromise between solar physics and human biology. First, the sun's emission spectrum is uneven. It naturally pumps out significantly more blue light than violet light. This chart shows the specific sensitivity of the photoreceptor cells, or cones, in the human eye. You can see a prominent peak showing that our eyes are highly tuned to detect blue light, but we are incredibly poor at picking up violet. Our brains process that uneven mixture of scattered blue and violet light and simply default to blue. The sky you see every day is an optical illusion, a quirk of solar radiation and human vision that can easily be disrupted. That illusion breaks down the moment the sun begins to drop toward the horizon. As evening approaches, the geometry of how light hits the Earth changes. As this diagram of the Earth shows, sunlight striking an observer from directly overhead takes a relatively short path. But at the horizon, that light has to cut through up to 38 times more atmospheric mass. Over that massive distance, the short blue and violet wavelengths are completely scattered away into space before they ever reach your eyes. The only light robust enough to survive the journey are the long, lazy wavelengths of red and orange. But atmospheric gas isn't the only thing altering the light. When water vapor condenses into clouds, we introduce a new process, Mie-scarring. Because water droplets are significantly larger than gas molecules, they scatter all wavelengths of light equally, which our eyes process as a bright, pure white. And when those clouds gather into a dark gray storm front, they haven't actually changed color. They have simply become so thick and packed with water that they physically block the sunlight from illuminating their bottom layers. The warm, glowing colors of a sunset and the dark, brooding gray of a storm cloud are physical records. They trace the sunlight's arduous journey, revealing the exact density and nature of the obstacles in its path. Sometimes